A transformer is a very useful application of some of the ideas discussed in this chapter. To motivate the idea of a transformer, let us consider a time-varying current that flows through a solenoid. In principle, any type of electric current that changes with time will work for what we discuss here, but in practice, we will nearly always consider AC current. So here's a picture of our setup. We have a source that produces AC current, and that electric current will flow through a solenoid. Because we have electric current flowing through a solenoid, there will be a magnetic field produced. The lines of magnetic field are drawn as these thin dashed lines. Because this current is changing with time, the magnetic field produced by the solenoid will change with time as well. Now, these magnetic field lines will fill the space surrounding the solenoid. I could imagine that if I were to take a second solenoid and place it close to the first solenoid, some of these magnetic field lines will pass through the loops of the second solenoid. Because we have magnetic field lines passing through the loops of the second solenoid, there will be a magnetic flux through the second solenoid. Because the magnetic field is changing with time, remember, we connected the first solenoid to an AC source. The magnetic field is changing with time. I expect the magnetic flux through the second solenoid to change with time as well. Because we have a changing magnetic flux through the loops of wire that make up the second solenoid, there will be some amount of voltage induced in the second solenoid. The amount of voltage induced in the second solenoid will depend on the number of loops of wire that make up the second solenoid and the rate of change of magnetic flux through the second solenoid, and that will be given through the equation we have been considering all chapter long. Based on this picture, as it is drawn right now, we will produce some amount of induced voltage in the second solenoid. But as a thought experiment, let's imagine if we could somehow magically take all of these magnetic field lines that pass through the loops of the first solenoid, and instead of having them spread out and fill the space surrounding the first solenoid, what if we could direct them so that they all pass through the second solenoid as well? Well, in that case, we would have a much greater rate of change of magnetic flux, and we could produce a lot more voltage. And it turns out that is actually possible to do. Magnetic field lines fill an environment that is composed of iron much more easily than they fill an environment that is composed of air. If we were to take a loop of iron and have that loop of iron pass through the interior of both solenoids, then we would have a picture that looks something like this. On the right side of this picture, we have our AC source of electric current that's connected to our first solenoid. Current will flow through this solenoid and produce a magnetic field. The magnetic field lines will be found within this iron loop, and the magnetic field lines will preferentially try to remain within this iron loop. Therefore, we could use this iron loop to direct the magnetic field lines so that they also pass through the interior of the second solenoid. If we expand this iron loop so that it completely fills the interior of both solenoids, we could almost ensure that all the magnetic field lines that pass through the first solenoid also pass through the second solenoid. In the real world, there will be a few magnetic field lines that leak out, but this effect will be very small for a well-built transformer. If we have the same number of magnetic field lines that pass through both solenoids, we could say that we expect the magnetic flux through both solenoids to be the same. And therefore, the rate of change of the magnetic flux through both solenoids should be the same as well. For a well-built transformer, typically the flux lost will be less than 1% of the total magnetic flux. Very often, the first solenoid, the solenoid that is connected to the AC source of electric current, is known as the primary, and the second solenoid where we create the induced voltage is known as the secondary. The voltage that is responsible for the AC current flowing through the first solenoid is known as the primary voltage. The primary voltage is related to the rate of change of magnetic flux with respect to time through the first solenoid by this equation. Here, NP is the number of loops of the first solenoid. As discussed previously, the induced voltage in the second solenoid can be given by this equation where NS is the number of loops in the second solenoid. Because the rate of change of magnetic flux with respect to time is the same for both solenoids, since the magnetic field lines are directed to pass through both solenoids, we could relate the primary voltage to the secondary voltage through this equation. Looking at this equation, we could see that it is possible to increase or decrease the voltage depending on what we are trying to accomplish.